Series-rated systems are often utilized in industrial and commercial settings. In series-rated systems, overcurrent protective devices, or OCTs, are connected in series with each other. These devices have different interrupting ratings. Specifically, the interrupting rating of the downstream OCT is less than that of the upstream OCT. In contrast, fully rated systems require that all OCTs in the system have the same interrupting rating as the source. The OCTs closest to the source may have higher current ratings than required, and this is to meet the interrupting rating requirement. In a fully rated system, all OCTs, including the main, must be rated for the same interrupting rating as that supplied from the utility. As an example, if the utility supplies 42K AIC, all OCTs in the system must be rated for at least 42K. It is possible to combine fully rated and series-rated systems. However, this requires careful design and coordination. In such a combined system, the series-rated portion would be located downstream of the fully rated portion. The OCTs in the fully rated portion would have an interrupting rating equal to or greater than the AIC from the utility. The OCTs in the series-rated portion would be rated less than the OCTs in the fully rated portion, and this is according to the listing. Series-rated systems have the advantage of potentially reducing the cost of OCTs, especially for large systems. However, a disadvantage is that they require more complex coordination studies. Fully rated systems offer the advantage of simpler coordination studies. The disadvantage of fully rated systems is that they can be more expensive than series-rated systems. The choice between a series-rated or fully rated system depends on the specific requirements of the installation. Series-rated systems can be more cost-effective, but they require more complex coordination studies. Fully rated systems are simpler to design and coordinate, but can be more expensive. We remember that combining fully rated and series-rated systems is possible, but it requires careful design and coordination. Let's delve a little deeper into the technical aspects of each system. Firstly, consider the interrupting rating, also known as the ampere interrupting capacity, or AIC rating. This rating indicates the maximum fault current that an overcurrent protective device can safely interrupt without being destroyed. The AIC rating is typically marked on the device. It is crucial to select OCTs with an AIC rating that is equal to or greater than the available fault current at the point of installation. Secondly, regarding coordination studies, these studies are essential for ensuring that the overcurrent protective devices in an electrical system operate in a coordinated manner. The goal is to isolate a fault to the smallest possible portion of the system, minimizing downtime and preventing cascading failures. In a fully rated system, coordination is relatively straightforward because all OCTs have the same interrupting rating. However, in a series-rated system, coordination is more complex because the OCTs have different interrupting ratings. The coordination study must take into account the characteristics of each device and the potential fault currents at various points in the system. The coordination study will involve analyzing time current curves for each device to ensure proper selective coordination, where the device closest to the fault clears it before upstream devices operate. Thirdly, consider the cost factors. As mentioned earlier, series-rated systems can potentially reduce the cost of OCTs. This is because downstream devices can be rated lower than upstream devices. The difference in cost can be significant, especially in large systems with many OCTs. However, the cost savings must be weighed against the increased complexity of the coordination study. Fully rated systems may have a higher initial cost due to the need for higher rated OCTs throughout the system. However, the simpler coordination studies can potentially offset some of these costs. Now, let's discuss some specific examples of when each type of system might be preferred. A fully rated system is often preferred in applications where reliability is critical and downtime is unacceptable. Examples include hospitals, data centers, and other facilities where a power outage can have serious consequences. The simpler coordination makes it easier to ensure that the system will operate reliably in the event of a fault. A series-rated system may be preferred in applications where cost is a major consideration and downtime is less critical. Examples include industrial plants and commercial buildings where a power outage can be tolerated for a short period of time. The cost savings from using lower-rated OCTs can be significant in these applications. Now we will explore some considerations when combining fully rated and series-rated systems. When combining these systems, it is essential to ensure that the transition between the two portions of the system is properly coordinated. The OCTs in the fully rated portion must be able to interrupt the maximum available fault current at the point where the series-rated portion begins. The OCTs in the series-rated portion must be coordinated with each other and with the OCTs in the fully rated portion. This can be achieved through careful selection of OCTs and through the use of appropriate coordination settings. It is also important to consider the impact of any future changes to the system. If the system is modified, it may be necessary to re-evaluate the coordination study to ensure that the system continues to operate properly. Finally, it is crucial to consult with a qualified electrical engineer when designing or modifying an electrical system. A qualified engineer can assess the specific requirements of the installation and recommend the appropriate type of system. They can also perform the necessary coordination studies, then ensure that the system complies with all applicable codes and standards, such as the National Electrical Code, or NEC. Now let's discuss specific NEC articles related to overcurrent protection and coordination. NEC Article 240 covers overcurrent protection in general, including requirements for AIC ratings and coordination. NEC Article 240.86 specifically addresses series ratings, and it outlines the conditions under which series ratings are permitted and the requirements for marking and documentation. NEC Article 700.27 covers coordination requirements for emergency systems, and it requires that the overcurrent protective devices in emergency systems be selectively coordinated to ensure that a fault on one circuit does not interrupt power to other essential circuits. Let's consider a scenario where a new piece of equipment is being added to an existing electrical system. Before the equipment is installed, it is important to determine the available fault current at the point of connection. This can be done through a fault current study. Once the available fault current is known, the appropriate OCT can be selected. If the existing system is fully rated, the new OCT must have an AIC rating equal to or greater than the available fault current. If the existing system is series rated, the new OCT must be coordinated with the existing OCTs in the system. It may be necessary to replace existing OCTs with higher rated devices to achieve proper coordination. Another important consideration is the ambient temperature in which the OCTs are installed. The AIC rating of an OCT is typically based on a specific ambient temperature, such as 40 degrees Celsius. If the OCT is installed in an area with a higher ambient temperature, the AIC rating may need to be derated. Manufacturers typically provide derating factors for their OCTs. It is also important to consider the altitude at which the OCTs are installed. The AIC rating of an OCT may be affected by altitude, especially at high altitudes. This is because the dielectric strength of air decreases with altitude, which can reduce the ability of the OCT to interrupt a fault current. In addition to AIC ratings and coordination, there are other factors to consider when selecting OCTs. These factors include the continuous current rating, the interrupting time, and the voltage rating. The continuous current rating is the maximum current that the OCT can carry continuously without overheating. The interrupting time is the time it takes for the OCT to interrupt the fault current. The voltage rating is the maximum voltage that the OCT can safely interrupt. When selecting OCTs, it is important to choose devices that are appropriate for the specific application. For example, in applications where nuisance tripping is a concern, it may be necessary to use OCTs with a time delay feature. In applications where high fault currents are expected, it may be necessary to use OCTs with a higher AIC rating. Also, consider surge protection devices. While not technically OCTs, surge protection devices, or SPDs, play a crucial role in protecting electrical equipment from transient voltage surges. SPD should be coordinated with OCTs to ensure that they work together to protect the system. SPD are typically installed in parallel with the load and are designed to divert surge currents to ground. The selection and installation of SPD should be based on the specific requirements of the application and should comply with all applicable codes and standards. Proper grounding is also essential for electrical system safety and performance. A properly grounded system provides a low impedance path for fault currents to flow back to the source, which helps to ensure that OCTs will operate quickly and effectively. Grounding systems should be designed and installed in accordance with NEC Article 250. In addition to the NEC, there may be other applicable codes and standards that must be considered when designing and installing an electrical system. These codes and standards may vary depending on the location and the type of installation. It is important to be familiar with all applicable codes and standards and to ensure that the system complies with these requirements. Let's now consider the impact of harmonic currents on electrical systems. Harmonic currents are currents with frequencies that are multiples of the fundamental frequency, which is typically 60 Hz. Harmonic currents can be generated by nonlinear loads, such as electronic devices, variable frequency drives, and arc furnaces. Harmonic currents can cause a variety of problems in electrical systems, including overheating of equipment, increased losses, and voltage distortion. To mitigate the effects of harmonic currents, it may be necessary to use harmonic filters. Harmonic filters are designed to reduce the amplitude of harmonic currents. They are typically installed in parallel with the load that is generating the harmonic currents. The selection and installation of harmonic filters should be based on a harmonic analysis of the system. Another important aspect of electrical system design is power quality. Power quality refers to the characteristics of the voltage and current in an electrical system. Poor power quality can cause a variety of problems, including equipment malfunction, data loss, and increased energy costs. To improve power quality, it may be necessary to use power factor correction equipment, voltage regulators, and other power quality improvement devices. Selection and installation of power quality improvement devices should be based on a power quality analysis of the system. Let's talk about arc flash hazards. Arc flash is a dangerous phenomenon that can occur when a fault current flows through the air. Arc flash events can generate intense heat, pressure waves, and toxic gases. Arc flash hazards are a serious concern in electrical systems, and it is important to take steps to mitigate these hazards. One way to mitigate arc flash hazards is to perform an arc flash study. An arc flash study is an analysis of the electrical system to determine the potential arc flash hazards at various points in the system. The results of the arc flash study can be used to select appropriate personal protective equipment, or PPE, for workers who may be exposed to arc flash hazards. Another way to mitigate arc flash hazards is to use arc flash mitigation devices. Arc flash mitigation devices are designed to reduce the duration of an arc flash event. These devices can include current-limiting fuses, arc flash relays, and arc flash circuit breakers. In addition to technical considerations, it is also important to consider the human factors involved in electrical system safety. Electrical workers should be properly trained and equipped to perform their jobs safely. They should be aware of the potential hazards associated with electrical work and should follow safe work practices. It is also important to have a written safety program in place that outlines the procedures for working safely on electrical systems. The safety program should be reviewed and updated regularly to ensure that it is effective. Regularly scheduled maintenance and testing of electrical equipment is also essential for ensuring system safety and reliability. Maintenance activities can include inspecting equipment for signs of wear and tear, tightening connections, and cleaning equipment. Testing activities can include insulation resistance testing, circuit breaker testing, and ground resistance testing. The results of the maintenance and testing activities should be documented and used to identify potential problems before they lead to failures. Finally, documentation is crucial for proper electrical system management. Complete and accurate documentation should be maintained for all aspects of the electrical system, including design drawings, equipment specifications, coordination studies, and maintenance records. This documentation can be invaluable for troubleshooting problems, planning upgrades, and ensuring the safety and reliability of the system.